and we're down to just under 2,000 Android only. And that's...
Which EAS version you're using?
So this is...
that is in mainline or still...
Yes, it's the one that's in mainline. So everything that's in 5.1,
yeah.
including your patches,
Okay.
are in 419 now. So originally 419 got the simplified energy model when it was still in review, and then it's been updated so it matches now.
Is Walt still in 419?
No, no Walt in 419. Not in Android Common anyway. So I thought it might be useful to try and split these up a bit and show how we think about them internally. So we generally consider it by functional group. So there's not very many of these functional groups, and it makes it much easier to think about what's going on. So if you think about purely the energy model and the energy cost wake-up placement, so that's the what you think of when you think of EAS, around about 80% of the pieces are upstream. So not the lines of code, just the pieces. Documentation actually forms quite a large part of the number of lines of code. So that's upstream in 5.1, but wasn't in 5.0. Then there's another group which can be considered to be the thermal capping group. Now, this is not actually very many lines of code in Android Common, but there's a huge benefit to upstreaming this because at the moment every vendor is using a different solution. None of them really use the solution that's in Android Common. I think PMWG is the only platform which actually uses this. So if we can have an upstream solution, the hope is that more people will use the upstream solution, and we're really depending on you here. And then another really large component of what makes EAS in Android particularly, not so much upstream, is a performance boosting framework called SCEDtune. If you don't know, SCEDtune allows you to define C groups and define a boost level inside that C group, which is it's a signal proportional correction value. So if you boost 50%, you get 50% of the remaining capacity added to your utilization. So it's easy to tune experimentally, but it's not easy to tune in reference to specific hardware topology. It's a more experimental interface, and it has a couple of other features as well.
Okay, so in 4.19 it's SCEDtune and not utility.
4.19 is SCEDtune. Oh wow, okay. 4.19 SCEDtune. So we have an idea to replace SCEDtune in the longer term. So that's not 4.19, okay. But so there's postings on LKML and have been for about 6 months now. Various different revisions of a framework called util-clamp, which is another C group. Well, it's not a new C group controller. It's an extension of the CPU controller, and it allows you to set minimum and maximum utilization values, which are then applied to tasks in that group. So that will account for, when that's merged upstream, that will account for roughly 1,500 lines out of the 2,000 we have. But unfortunately, the upstream version doesn't exactly replicate what we have in SCEDtune in Android right now. Only the task boosting for frequency selection. And then there's a bunch of other pieces where we don't currently have an upstream alternative. So probably the largest one of these is called find best target, and that's a function we use to restrict the CPU candidates that we then go on to do energy diff for. So that function, find best target, it implements two algorithms. Well, actually, it implements a number of algorithms, but the main two are it finds a performance target and an energy target using some heuristics, and then we use one or other of those depending upon the boost configuration of the task we're looking at. And it also uses the boost configuration of the task to try and start its search on different CPUs to try and minimize latency where we need to. So I mentioned SCEDtune. So one of the pieces that's missing in util-clamp that SCEDtune provides is a concept called prefer idle, which I'll talk about in a bit. And another thing which we call boosted task placement, and this is basically just using the boosted utilization of a task when we decide where to put it. What that allows you to do is it allows you to boost the task and then make sure that it doesn't get placed on very little CPUs, that kind of thing. Something else we don't have is an equivalent to schedule and hold. We'll talk about that in a moment. And then load balancing, tracing, schedule till, and then the last one is a wake up optimization.
What the last one is doing exactly?
I'll tell you in a minute. It's really good. So, I jumped ahead of myself. Look, find best target's got multiple algorithms. So the upstream EAS algorithm is slightly different to this. What the upstream EAS algorithm does is for each frequency domain, which is big enough to hold the task, where the CPU capacity is large enough, we find the CPU with the lowest utilization and we select that as an energy candidate. And then what we do is compute the energy for the task on each candidate CPU and select the lowest cost option. So this is actually pretty close. It works differently, but it turns out to be pretty close to what find best target actually does. So it's using a different set of heuristics. But the eventual CPU selection is almost identical.
So why do you want so you really need to find a solution stream for this find best target missing feature?
Well, so I think the solution is going to be to remove it. There's a couple of things missing upstream. We don't have a concept of prefer idle and boosted task util, but the other parts of find best target are probably replaceable with. So now upstream we have an energy aware wake up path, which didn't exist when find best target was written. So we're going to switch to using the upstream energy aware wake up path, So the idea is that we add two small pieces of code to implement prefer idle and sked tune boosting in the mainline wake up path. That's one patch of about 40 lines of code, I think. And then that allows us to, oh, by the way, that also adds, so we've got some C-state tracking in Android. So when we select an idle CPU, we select the one in the shallowest C-state. Instead, what we can do is select the one with the lowest exit latency, which corresponds to virtually the same thing, but it means we don't need the same access to the CPU idle framework anymore. There's now a new interface where this information is exposed, so at the same time we can change over to using that instead of using the outer tree C-state stuff. Yeah, so we add...
There, what you want is, so it's really about the exit latency that you're interested in?
So what we do is when we have a bunch of otherwise identical CPUs we can choose from that are all idle, we want the one in the lowest idle state because theory is we want the one that's going to wake up quickest. So really the actual metric we were looking for was exit latency. It's just that it wasn't available back then when we originally wrote prefer idle was probably 318. There is, yeah. But that doesn't work on ARM platforms because it's at a different part of the topology level. So anyway, we add these two pieces to the mainline energy aware wake up path, and then we already had a sked feature in 4.19 and also in 4.14 actually to switch from using find best target to switch to using the mainline wake up path. So the plan is add this feature, switch the shed feature default, so we switch to the mainline path by default, and actually so we merged this last week. Actually, it was unexpectedly acceptable. I might show the test results in a minute, but essentially the test results are indistinguishable. So we run WL tests on a Pixel 3 device, and there's no statistically significant change except for in the media playback we save 3 to 6% energy, and on the home screen idle we save 5% energy. Other than that, in the performance use cases, there's no statistically significant difference. So that was quite nice. So the idea is that in 4.19, the default has just changed. but the code is still there, so anybody that's already got base ports that have hooked into find best target for something else, don't have to worry about that. They can just change the default back, and off you go, no problem. But in whatever the Android Next is, and probably in the experimental version very soon, we won't have find best target included at all. And actually, one other point to make is that this prefer idle business in step 1 here, as soon as we can come up with an alternative to this which works upstream, we won't have this either. So, speaking of prefer idle, this is just a C group attribute, so it's basically a flag that we mark on threads that belong to the top app and the foreground C group. And obviously, if we don't have sketch unit, it disappears, so we have to come up with an alternative. The first alternative that we're investigating at the moment is basically get rid of the whole concept. So why we have prefer idle is largely to try and it works in conjunction with the CPU sets that we use in Android to try and ensure that the heaviest application threads like the UI thread, the render thread, get to run on a CPU which is idle, which is more or less reserved for them by the CPU sets, and that way we try and minimize the chance of them being preempted. So it's really all about wake-up latency and preemption resistance for those important threads. So given that we already look for the max spare capacity when we use the simplified energy model, this is one of the prefer idle behaviors anyway, so we can probably just do this for everything. And we already use boosted utilization, so if you set your min util on util clamp to an appropriate level, you can guarantee that these tasks only run on the big side or middle side or whatever. And actually it turns out in Android 4.14 when we go for these idle CPUs we don't actually look at the block load. So, and actually maybe the fact that we try and choose the lowest exit latency means that we do hit CPUs which are more likely to be woken up again. So making this change might actually help things out. And finally, one of the main tasks which we were trying to prevent preemption from has become an RT task. So that's perfect. CFS can't preempt that now.
Okay, so yeah, so this prefer idle was mainly to link to the display path and the surface.
Yeah, it was really all about making sure that the UI thread and the display path worked without interruption.
So you keep the IO stopping, right?
So that depends on PowerHow, what it does with an interaction hint. It doesn't always keep the highest OPP.
With direct task? And schedule?
Not in Android, no. In Schedutil normally you would, but in Android we don't. In Android we use Vincent's RT signals, run Q signals. That's actually, I've been investigating putting the entity signals back in because there's some interesting stuff. Maybe we talk about that later. So of course, it's not a definite that any of that's going to work. We have two backup options. The first one is to try and combine the task policy, so the sched policy, and maybe the priority or shares or some kind of other attribute to infer is prefer idle required or not? Do we need to change behavior or not? And then if that still fails to provide the user interface guarantees that we need, then backup option number 2 is to try and persuade upstream that we have a problem here that we can't solve by pushing tasks into other sched classes. Now I think that's going to be a tricky thing because the answer is usually if you don't want to be interrupted by CFS, use RT or use deadline. And potentially the answer upstream might well turn out to be deadline C groups or something in that matter.
Have you tried to play with the skid slice value?
Not yet, but it might be interesting to increase the sked slice for these tasks.
Because that's what what I have seen. So I have a training tomorrow, and I have noticed that while preparing that, is that if you have two tasks with the default priority by default, you will run 12 milliseconds pre-tick before switching to the other one.
Really?
It's
Okay.
not every tick. If your increasing the next priority, because the burn time is increasing,
Mm-hmm.
you start to switch between those tasks much more often. So maybe it's, one of your problems is that the skate slice on the 8 core, it's 12 milliseconds. No, it's 24 milliseconds. So when you have two tasks, it means that you can run 12 milliseconds before switching to the other one. And 12
Maybe,
milliseconds
yeah.
compared to 16 is quite a lot.
It
So
is
if
quite a
you're
lot.
unlucky and someone is already running, you will have to wait.
You have to
at least
wait.
12 milliseconds. before
It's
you-
pretty unlikely that you can complete the frame render in 4 milliseconds at the end. Yeah.
So playing with the skate slice, maybe you can preempt the other one earlier, which means that
And
you will
still hit your
progress
deadlines, but not worry about preemption so much.
Yeah,
Yeah.
yeah. So you will be able to start running earlier, and if you have some dependency, everything can start running earlier.
Okay, I'll ask Dietmar to look at it.
Yeah.
This prefer idle replacement is in his box of stuff. The next thing missing is the boosting. So we've got util clamp that we're pushing for upstream, and util clamp lets you define a min and a max utilization level. Now this is absolute capacity values, so you can define a 256 min and a 728 max, and your CPU, your task utilization will be clamped to those values. So it's pretty clear how it works when you look at a system, and you've got a system with CPUs at various capacities, and you can see how they all fit together looking at the topology. So it ought to be easier to tune, but it's a completely different concept to SCED-tune, so it's all going to have to be done again from scratch. And then, so the first upstream version of util clamp only influences the frequency selection, and we want to use it to influence the task placement as well. So what our plan for that is, we do it in Android, we prove it works, and then we try and upstream that as well. I was going to say something about the tuning, but I forgot what it was. Oh yes, so in Android 4.19, if util clamp merges upstream before the summer, we're going to backport it to 4.19, but we're not going to remove SCED-tune. So we want to use 4.19 to figure out how to tune it in a way that matches SCED-tune. So that will be a high key 960 type exercise. And then there's one more thing in SCED-tune which we don't really have a solution for upstream, and that's a feature called SCED-tune hold, which I know quite well because it's a hack of mine. So it's essentially we had a problem where we would have RT tasks which wake up and go to sleep quickly enough that you've changed frequency in SCED-util, and then you're not able to ramp the frequency back up when the task wakes up again. And if those boundaries align just correctly, you end up not being able to satisfy your RT requirements. So we have this SCED-tune hold thing, which allows you to keep a boost active on a CPU for 50 milliseconds minimum amount of time. And by default, we only apply that to RT tasks. It actually turns out to be quite simple. It's just a bunch of timestamps that you collect, and when you do an update, you check to see whether it's expired or not. But the main thing it does is it covers cases where it's actually not possible to know this stuff ahead of time, and the fact that you've got those frequency change restrictions means that you can get yourself out of phase in a way which causes you problems. So it covers up all of those issues, which is why it's still in Android. So we don't really have an answer to this. So I have an idea, maybe we could put it in SCED-util instead, but I don't know. Yeah, in a similar way to IO weight boosting. Maybe we could reuse the IO weight boosting.
So can you explain the policy one more time? So basically this is every time an RT task wakes up.
So
for the next X milliseconds.
every time an RT task wakes up, which belongs to a SCED-tune group with a boost active, so not all of them, but like top app tasks, if you have an RT task which wakes up, we record the timestamp when it wakes up, we activate boost on the CPU, and whenever we call from SCED-util, whenever we call boosted CPU util to figure out what frequency we should be using, that boosts remains in place for a minimum of 50 milliseconds. And obviously every time the task wakes up, we extend it. And then, so I mentioned load balance tweaks. There's 5 of these. Actually, I don't really want to talk about these very much because most of these cover problems we used to have which don't really exist anymore in upstream. And since we have upstream almost entirely in Android 4.19, there's we're still going to check whether or not there's any impact. But at least in the first 3, there's no impact on current 4.19 code line. So those will definitely not be appearing in the next Android. The bottom 2 might appear or might not, depending on the continued testing. But I don't think there's any. We expect to get all of these out. If there's anything in there which is still having an impact, then we'll fix it upstream. These all originated in Android before Misfit was upstream. So. Okay, next section, trace and debug. So I said we had 2,000 lines of code, of which 1,500 was git tune. Then probably 300 of the rest are trace points and additional debug information. Now nobody really cares about this stuff unless you want to prove that EAS is working properly. So we don't really want to put these in mainline. There are a couple of things that would be very interesting to put in mainline, such as the overutilization flag, and maybe some flags about, maybe some trace points about how much energy the system's calculating. So I think those would be useful upstream. But Peter's already said that he doesn't want any new trace events. It's a new user space API. So this is really a call for ideas. We are looking at using eBPF with trace points, which are raw trace handler events, but actually it turns out to be really hard to hook code to those things that can run.
Oh, really?
Yeah, you can run, but you don't have access to any kernel stuff. You basically just get a point at which you can run an eBPF program.
Normally you should have access to some...
You only get GPL symbols, and what we want to trace is not in the symbol table, so we can't call it.
I think this can be... Leo is not there because I think Leo has a...
Leo Yan can give.
Okay,
Because you
so I should ask Leo.
Yeah, Steve Rostedt has some, I think his presentation, from ELC last year, or maybe the year before, talks a lot about using eBPF trace points.
So we can use eBPF and we can inject trace points. We can inject stuff straight into the trace buffer. The problem is that we can't get access to the parts of the scheduler code that we want from inside there.
He's talking about that sort of stuff as well,
Okay.
from what I remember. You might need a copy of the debug symbols for the kernel with the debug symbols.
Right.
You can use to work out where those things actually are. You might not be able to do it with just the running kernel binary.
Okay.
I think you can't do it with the running kernel binary alone.
Yeah, so that was one of the
I think,
things
yeah.
was to be able to do this on signed vendor kernels.
So long as they can give you the debug binary.
Okay.
I mean, assuming that's all you need, I'm missing something, but I'm relatively sure.
I think that from what I understood, any function should be able to be hacked by eBPF.
I think
As long as you have
any exported
the
function,
IP address, yeah.
any exported function you can
No.
get, isn't it?
Yeah,
Or is it any function you can get the address for?
Yeah.
yeah, exactly. Exactly.
If you know the address and the function signature, you can call it. Yeah.
Or if the function is inlining your
Yeah, well-
should be able to hack that.
Okay. Well, maybe so.
If you can't do it, the eBPF people are probably interested in helping you do it. Is the other bit of it. I mean, that's the sort of thing this is the glorious future. Although then, of course, this all becomes an API itself, and
Well, yeah. So there's an open question there about whether or not we're just inventing a new API, which you have to
Yes.
compile code against instead of
yes.
run tools against. Yeah, so we could actually just maintain an out-of-tree patch set, but that's obviously a pain in the ass for everybody, so we don't want to do that. So another point is actually we don't need most of these to run Lisa tests, but figuring out what went wrong is very difficult if you don't have these.
Do you know if Schedutel, is that under the purview of Peter Z's edict of managing trace points, or does Raphael maybe have a say?
Raphael might be a little bit more persuasive, but since it's in the scheduler, I think Peter's pretty keen on making sure it conforms to his requirements.
The scheduler people have been burned before, so they're paranoid.
Yeah, there's a lot of trace points in the scheduler which you can't change and don't necessarily contain as much useful information as they used to 25 kernel versions ago. People have built enterprise monitoring systems based on them and things like that, and yeah, it's just a mess.
Yeah, there's some work on improving the user space interfaces for working with trace points, which is designed to mitigate this, because if they can convince people to use libraries that will do things like detect if trace points are there and handle them not being there better, then it's less likely that people will make tools that just completely die horribly if the trace point's missing, like happened to the scheduler people. So there's some possibility the situation might improve from that angle as well.
Okay. Yeah, well, we try and make Lisa gracefully degrade if not all the trace points are there.
Yeah, which is good programming, but not everybody does.
Yeah, especially if you've written your tool in C, because it's actually quite difficult to nest it that far.
Yeah, which is what the library's supposed to help with. It's supposed to hide.
So I see Stephen's been working on Python interfaces and an embedded C library interface for trace commands.
Yeah,
so
that's
why, is it?
That's the effort. Yeah.
It did have a Python interface in the old version, but it was really quite difficult to use. So I don't think anybody used it much. Okay, well, can we have a chat later on, Mark, about eBPF and who the right people are? And, yeah, because I mean, I don't know. I mentioned Schedutel, so we have a couple of hacks in Android. We use the CPU run queue signals for RT task util rather than go to max. I don't think we can avoid doing that. It's way too expensive in Android to go to max all the time. I mean, it's on the order of 40% increase in energy consumption for media cases, so we just can't avoid that. And we also have a patch which splits the rate limiting into a separate up and down rate limit. So the idea behind that is that we make it easy to increase frequency and harder to decrease frequency. But actually, since we've got the sketune hold stuff in the RT patches, everybody just sets those the same now. I haven't seen a device for quite a while which had different values. And then there's another thing that we're actively working on right now, which is to switch the way Schedutel evaluates frequency selection over to using the upstream energy model. So we calculate what the energy cost is of running at a certain frequency, and then we have a small energy margin which is allowed, and we select the highest frequency which can still fit in the energy margin. So hopefully this will allow us to ramp up frequency more quickly when a task wakes up. That's essentially what it's for. And also to skip inefficient OPPs in voltage curves.
So you're using the energy model?
So we use the energy model. One of the things that the energy model framework can tell you in mainline is what the energy cost is for running a certain utilization at a certain frequency. And it can tell you the energy cost for the whole performance domain. So in Schedutel, what we do is we take the frequency, we take the utilization value that the CPU has, and we say, okay, assuming we select a frequency linearly scaled, map that onto a frequency, the nearest highest frequency. What does that cost in terms of energy to run the cluster at that? And then we say, add an energy margin on top of that, and then we say, okay, next OPP, next OPP, next OPP, and figure out what the highest OPP is that fits inside the energy margin that we've got. This actually combines really nicely with your patch. So,
what is that energy margin? How do you get
well, at the moment it's just set at 20% because we used to set a 20% utilization margin. that the actual margin is probably something that needs to be tuned.
Is that
And
a knob that'll be exposed?
ideally not, but probably. Probably expose it in Android and not in mainline. So the idea here is basically when you see when you see an energy curve which is kind of flat and then goes up, the idea is that we don't bother going through all of these OPPs as we rise up. We just go to something that's going to give us a reasonable return on our investment, and then follow the curve as normal. So this is something actually Peter Zylstra asked for as a justification for including the energy model a long time ago. So we're pretty confident that it can go upstream when it's ready. But that'll go upstream, and then we'll probably backport it to 419, and it'll definitely be in the next Android. It might be behind a config switch or something in 419 because it's a change for folks. So. And then, so something I've noticed looking at 414 based public kernels is that, do you remember on the interactive CPU freak governor, it had this array of values you could provide called high speed load. And it was basically when you get to a certain utilization, go to this frequency. Next utilization, go to this frequency. So people have been re-implementing that in Schedutil with exactly the same interface, with exactly the same behavior, which I found interesting because I've seen it re-implemented at least twice, actually, independently. So maybe we need something similar to that. Maybe that's feedback we should take account of. I don't have a strong opinion on it. I'm kind of hopeful that we won't need to do it if we do the first one. And also you see finer granularity tuning. Now this refers, I didn't really call it out directly here, this refers to being able to set different energy margins for different clusters and different frequency margins. So typically we use 20% as the frequency margin in Schedutil. A bunch of implementations use add a new sysfs file for that and allow you to set it on a per cluster basis, which is kind of interesting because it means you can be less aggressive, more aggressive on the little CPUs and less aggressive on the bigger ones. You can tune it to match how expensive it is to move up the curve. So maybe that's also something we need to consider for upstream. I don't think Peter will like that. It's an extra user space knob, but
could you work out what they're trying to do with that? Like you're saying, maybe
yeah, I'm hopeful that the energy model version that we implement there might cover all of these use cases. If anybody in the room has implemented this and could tell me why, then maybe we can try and extend the testing for the energy model thing. No? Okay. And then the last thing that we have is this wake queue optimized wake up placement. It's in Android 4.14, it's in Android 4.19, it was in Android 4.9. So it's been around for a while. Actually, what it does is it adds a little bit of information to the try to wake up call into the scheduler, so that when we have a wake up primitive which knows how many waiters are going to be woken up, it can pass that information to the scheduler. So it can say, I'm waking up and there's 7 more to come after me, to the scheduler. And this allows the scheduler to do its wake wide thing straight away, essentially. So this used to be very useful for us in 4.9. It used to work really well. It used to be very useful. It used to give us probably a 2% improvement in Geekbench multi-thread performance. But that's no longer the case. So the scheduler has got better and better at figuring this stuff out for itself. So that's no longer the case. And actually with the code the way it is in 4.19, the config flags are set up so that this doesn't actually provide any impact at all. It doesn't get used. We don't have the time to wake up queue flag on, so it doesn't propagate. So actually what we're planning to do with this is just drop it from the next Android and open up the discussion upstream and see if, see if anybody thinks it's a reasonable idea or if it's really stupid. I mean, what do you think? It's context that this kernel has that it doesn't use,
Yeah.
but it doesn't cover all the wake-up primitives. It only covers some.
The NSI of, and even that, so we were discussing this morning about something similar. The problem is that you can be in situation, you can have the same event. The problem is always that you can have the same event pattern but with different scale, and that can make sense for one pattern and time scaling or time timing, but doesn't make sense for another one. So just the event, I'm not sure.
This
just
is
having
really
the
just
event
for
is-
this is really just for fork bombs.
Yeah,
Basically, you've got to,
exactly.
and it's really common in benchmarks,
Yeah.
and it's quite common in stuff like Snapchat's video processing thing. It'll start a whole bunch of threads all at once, and they all need to start working straight away. But outside of that application, it's pretty rare.
She also said that the day scheduler's gotten better dealing with this.
Yeah, definitely. It goes into wake wide more easily. So the heuristics which implement this in the scheduler I don't think the heuristics have changed very much. I think our topology description now more closely matches what they expect. Yeah, it's precisely. It wasn't. Yeah. So it used to require more tasks to wake up than we had CPUs, and it doesn't do that now. So the wake wide flag returns true more easily for us now. That's the thing in the mainline kernel which prevents this from being a problem when you run Hackbench. Yeah, so anyway, this is in Android. If you wanted to have a look at it, it's in Android. It's called WakeQ something or other. It's quite invasive because it goes all the way from the wake-up primitives through the core scheduler right into, and it has to get all the way to the skate classes, of which CFS is the only one which does anything with the information. So I think chances are low that we'll get this exact patch set upstream, but maybe the idea is worth discussing. Okay, that's my last slide. Well, not quite my last slide. Discussion?
So you're
Questions?
quite close to have everything in mainline. So for the next,
Pretty close, actually. Pretty close.
what will be the next kernel version for Android after for that 19?
Well, looking at history, it tends to be whatever the LTS version is in the next year. So, who knows? 5.4, 5.
So you will directly use a 5.4 mainline kernel?
It should be possible to build a reasonably well-behaved device, I think. There might be some. If I go back to the, list of stuff. There might be some bits. There might be some code here that we do. There might be some code here that we do, and maybe we might have to introduce one of these similar kind of frequency holding hacks in Schedutil. But I'm hopeful that if we have the energy-based frequency selection upstream, we won't need it. Hopefully we'll have selected a high enough frequency that it'll be okay. And also, if we have util clamp and we're tuning directly based on utilization values, it might be easier to make sure that the tasks that you care about don't run on CPUs which are going to cause you problems. Yeah. So I should have come up with a lines of code estimate, shouldn't I, really? I did that once before and we nearly hit it. So I think my estimate was 2,000 at last year's Hong Kong Connect. I think my estimate was 2,000 lines of code. If I had to pull a number out of somewhere, maybe 400.
Okay. It's recorded.
Yeah. 400. Don't hold me to it, please.
So will EAS go upstream first, or will RT go upstream first?
EAS is almost upstream.
So is RT, they say.
Maybe we should start a race.
Yeah, that's what I'm suggesting.
Loser has to buy beers.
And are you working on some deadline C group stuff?
So we're not actively working on it right now. We see it as potentially a very useful thing, especially in the Android user space. So at the same time as all this has been going on over the last year, the Android user space has been being prepared for maybe util clamp changing underneath it. So we hope that the Android user space that's in master now is at least changeable by the OEMs to use the other mechanism. It's published, it's public. If you're following the right projects, you'll have noticed those patches go in, but it's really for experimentation at the moment. Okay, well, I guess it's time to get a cup of coffee.
I see so.
Thank you.
Thank you.